Hey, Core C++, it's great to be here. A few years ago, I gave a talk in this conference about a new compilation framework named MLIR, which stands for Multi-Level Intermediate Representation. I'm glad that today Omer and I can present some of the things we do with this technology to speed up the Intel Gaudi deep learning accelerator. The work that Omer and I will be presenting here today is the work of many engineers. Some of them are listed here in the slide, but there are many others, since working on this compiler is a joint effort of teams across the world. We are aware that not everyone in the audience are compiler engineers, so we'll give you all the background you'll need in order to enjoy the talk. In fact, we feel that maybe some brave data scientists can enjoy the talk as well. What are we going to cover today? We're going to take a look at compilation for deep learning, how we take a big model or workload like ChatGPT or other names you know, and compile it into a specific optimization execution plan, optimized for a specific hardware, in this case, the Intel Gaudi. Then we will introduce the TPC fuser. It's a just-in-time compiler for deep learning kernels that delivers a great performance for the Intel Gaudi. Lastly, we'll see some case study that Omer will present of some of the recent challenges that the large language models brought up and how we adjusted this compiler in order to continue being performant. But first thing first, what you see here is the spec and the block diagram for the Intel Gaudi. In opposed to homogeneous systems, this system is heterogeneous, which means it has multiple engines and of a few different kinds. One of them is the MME, a matrix multiplication engine that is dedicated to a lot of the workloads that deep learning has. The other one is the TPC, the tensor processor core, and also there are DMAs. For the Intel Gaudi 3, we have 8 MMEs and 64 TPCs. And with these multiple engines, with the right software, we can get efficient and performant work for a relatively small chip. So let's dive into that a bit. The MME, the matrix multiplication engine, is a piece of hardware that is doing all the heavy lifting that prevails in a lot of deep learning topologies of the matrix multiplications. It's very efficient, it's configurable, but not programmable. And the TPC is fully programmable. That's the core that do all the non-gem operations. It is a very long instruction word with vector pipes, scalar pipe, loads and stores. And it is fully programmable with a language named TPC-C, which is C, but with some dedicated types to work in a single instruction multiple data manner, in vector manner, for all the different types, ints and floating points for 1 or 2 or 4 byte types. And obviously it is programmable in a similar way to C code or C++ code that you know of, with a dedicated compiler that is a Clang-based compiler. And this is the Intel Gaudi software stack. We don't need to get to know all of it. You can just note that there are multiple compilers here, multiple libraries here, and you can also see that if you take it top down, the higher levels are closer to the data scientist code, such as PyTorch, and as you go down the stack, you're getting closer and closer to the hardware. But what does the graph compiler exactly do? What is compilation for deep learning? So let's just do compilers 101. I know most of you know everything about compilers, but let's just generalize that. A compiler is a piece of software that takes some source code and usually outputs machine code. It does two main things. One of them is transformations. Obviously, you take a high-level code and you output some machine code that will usually be much more efficient than the one that the user wrote. And in this process, it also does a lot of transformations, mainly to do optimizations. So here, this example, you know, on one side you see some C code, on the other side you see the assembly for x86. Two more words that we may be saying is LLVM, probably all of you know. It stands for low-level virtual machine. But actually when people say that, they mean a group of compilers. Specifically for us, the front-end are Clang or C language for all the language families. So that's compiler, we know that. But how it will look like to compile something for deep learning. So you don't just take ChatGPT and compile it into one binary that will be executed on the machine. Actually, what you have, on the one side, you have the topology. It will be transformed to a really big computational graph. And then the graph compiler will process that and will output a specific, very optimized execution plan for all the engines and all the things you need to configure in the device. So there's one big compiler, the graph compiler, but also within the system and the software stack, we have the Clang-based compiler that takes small pieces of softwares, deep learning kernels, we call them, for example, small primitive operations, mathematical functions, or anything that you want to write specifically to manipulate tensors. And it will be compiled with a Clang-based compiler. So that's already two types of compilers. And if we'll take a look at it visually, sometimes it helps. We're going to take some code, have an internal representation for that within the graph compiler. As we probably remember, the tensors that it will be working on are really big, and they will be probably processed across all the engines. And one of the first things we need to understand about Gaudi is that some will be executed on the MME, very fast, very efficient, right? The hardware dedicated for these operations, and the rest on the TPC. So what does the TPC have? It has, we said before, it is fully programmable with a language called TPCC, and we have a Clang-based compiler for that, and there are multiple libraries of kernels that you can choose from, and you can integrate within your topology. Some of it is pre-compiled, either the Intel Gaudi optimized kernels, that everything that a data scientist writes has some binary representation for it, compiled in a very efficient way, highly optimized. And the second one is you as a customer can write your logic, I don't know, all the secret sauce, pre-compile it, and you also have these kernels, and you can use all of them in your topology. In addition to that, we have a just-in-time compiler that on the fly, you see graph compiler is here above. Graph compiler will pass all the computation on graph, and this JIT compiler, the TPC fuser, will try to output as many binaries as possible, optimized for this specific topology. So after the small compiler finished running, it will yield an additional TPC kernel libraries, and now graph compiler can choose any one of these. So if we're going to sum up the graph compilation flow, graph compiler will receive some big computational graph that represents a deep learning workload, a deep learning topology. It will process it and will allocate all the operations to any one of the engines. It will generate specific configurations for the MME according to the specific graph, and then it will select all the kernels it needs from the different kernel library providers. So now when we're looking at this graph, we see already 3 different compilers. One of them, the TPC compiler that is LLVM-based, and we use it before the graph compilation, the graph compiler itself, and the TPC fuser, the just-in-time compiler that will add some more binaries to the mix. Then obviously graph compilers need to do optimizations like any other compiler for the entire graph, schedule operations across all the engines, taking into account different types of memories or constraints, and configure the hardware and all the different registers and the settings and everything it needs to do. And if we did a really good job, that's what we're going to see. This is a print screen of the Intel Gaudi profiler. What you see here, all the lines, are the different engines. On the top, you see the MMEs, the matrix multiplication engines, and all the workloads that are being scheduled and worked for them. On the bottom, you'll see the TPC. And in the middle, all the colorful and very nice blocks are actual workloads being executed. You can also note that they're all tightly packed, really neatly ordered one after the other. all the engines are being utilized, and they work in parallel, all the engines together. You can maybe also note that there's probably maybe some dependency here, maybe some workload needed to finish running on the TPC before it will start running on the MME, but that's really an ideal workload being executed. This is not done by magic, it's done by logic. There's a lot of logic within the graph compiler that is designed to do partitioning of the data, right, on the big tensors, the big matrices that it will run upon. So to partition the data in the right way and to group the operations together such that it will achieve this overlapping of all the engines in an efficient way and also utilize the memory as best as possible. Okay, so I introduced this compiler, but I don't think I convinced you why it is so critical for performance and what we're getting out of it. So if we take a look at the graph on the right, we'll see that if we're going to have small kernels, each one of them computing one of these operations, what we'll need to do is to load tensors from memory, do the computation, store it to memory, load it again. Let's say we have here a multiplication and then an additional one, and addition or some functions. For each one of them, we'll have to load all the tensor from memory, do the calculation, store it, and do it again and again in a chain. If we had one binary that could represent this entire subgraph, small computational graph, then we can only load all the inputs to this graph, do all the calculations, one after the other, while the intermediate results are being stored within the TPC registers, and then only store the output to memory. You can immediately see that we save a lot of HBM bandwidth for that. And also we don't have to allocate all the tensors. And there's also some additional optimizations that sometimes a just-in-time compiler can maybe yield a more performant code because it has specific information about the shapes, maybe about constants. So it can do optimizations that maybe you couldn't do on each and every one of these operations. Currently, the TPC fuser supports element-wise operations, reductions, and normalizations. And it's good that I can tell you theory, but these are actual graphs that we use to measure ourselves and to see the impact that this component does for the entire system. What you see here is the ratio, the speed up, between when you run these workloads with this just-in-time compiler and without. And you can see that the speed up is critical. It's not just a nice to have, it's critical for the entire performance of Intel Gaudi. These were measured on Gaudi 2. Okay, so we understood the context. We have some motivation for that. How is it done? So it is done in two parts. One of them is clustering. You got a really big computational graph and you need to designate small subgraphs and say that's a candidate to be a little binary, to be a fused kernel. And then you have the code gen process where you go over the pipe and you generate your code. The TPC fuser is using the MLIR technology, and the output of the input is this computational graph in some representation, and the output is LLVM IR. And when you take this LLVM IR and you compile it with the TPC Clang-based compiler, you get the binaries. So let's take a look at the main basic blocks for that. I guess whoever is familiar with compilation it will be familiar to them. So here we see a small graph of two operations only, just for the example, an addition and a scene operation. And what we want to do when we get this graph is to say the graph will now execute one binary, fused kernel number 1, and the semantics of it will be both operations together. The first thing we need to do is loop fusion, where the compiler merges multiple loops with the same iteration range into one single loop. And it makes sense, instead of going over everything, if we could analyze and see they have the same shapes, we can now have them running one by one. As we said, the intermediate results are being stored here. Makes sense. The next thing is, like any other systems that process so many data, we do it in a single instruction, multiple data manner, so it means it's vectorized. So the compiler can analyze the type of the elements, and it knows the size of the TPC register. It's 256 bytes. And according to that, it will know how to group together, how many elements to group together, so we can work in a vector manner. So here, it's a F32 type. We have some outer loop that we want to vectorize. We're going to vectorize it. In this case, it's going to be 64 elements. So this is vectorization. We also can do loop on roll, which means that the compiler will combine operations from consecutive iterations and will merge them into a single iteration. So if before this was one execution, now we're going to do two within the nested loop. Here, it's an illustration of unroll factor 2, but we can have other unroll factors, in this case, unroll factor 4. You can see that in this small case, we even did a fully unroll. One of the loops just got out because we could fully unroll this dimension. It saves some of the indices, but actually what it also does is that it hides latency of the hardware. So we get really good performance improvement from that. And the last thing is parallelization, right? Because we said that the workloads are really big, the tensors that we're processing are really big, and if we're going to compile something statically, then only one TPC engine will be able to run. And what we want to do, we want to give the graph compiler the freedom to allocate different parts of the work on different engines, different parts of the tensor on different engines, and we need to have a way to let him do that. And it is done by transforming the constant bounds of the loop variables into the constant bound of the loop into variables, so they can be dynamically allocated. And that's how it will look like, right? This is a small program that if we would have compiled it, it would have need to run over all the iteration space in a constant manner. And we don't want that. So this is exactly what this thing does, and Graph Compiler can now take this small binary and have a lot of instantiation of that according to the execution plan and however he will feel that will be best for this specific workload. Okay, so we know the context, we know the TPC fuser, but we want to give you some feel of what are the recent challenges that the deep learning domains always bring up, and how does it feel like to develop for this component. So Omer will present next.
Hi everyone, it's great to be here today. Thank you for coming. Today I want to show you a study case of a new operation that we needed to add to our code base. And this operation is called triangular softmax. In general, a softmax is an operation that takes a range of arbitrary values and transforms them into probabilities. You can see that on screen. That means that all of the inputs are non-negative and all of the outputs, are non-negative, and they all sum to 1. And triangular softmax is meant for large language models challenges, and specifically one of the main challenges of these models is to predict the next word in a sentence. So they take a sentence and they form all the prefixes, all the sub-sentences if you'd like, and feed them to one matrix of data. And then we have to compute a softmax for each of these words. So you can see that all the data above the diagonal of the matrix is not relevant. Moreover, you can think about it that if it was relevant, so you can use the future in order to predict the present, which is not allowed. This is not something that happens. So the main challenge here was not to implement softmax, because that's one thing we already have. The main challenge here was a new kind of data access pattern, which is a triangle access pattern. You can see on the left the traditional access pattern, 2 loops nested each other with constant bounds, and on the right there's the triangular data access, where the loop inside is dependent on the induction variable of the outside loop. And I'll show you today 4 challenges that we had in 3 different levels. I'll show you correctness challenges, performance challenges, and fusion challenges. Starting the first one, vectorization. So Dafna just a few minutes ago talked about vectorization. And this is what it looks like for the traditional case, for rectangular or regular operations. We have note that the vectorization is done on the J loop, on the innermost loop, and we take a loop of scalar operations, scalar data, and we transform them into a loop of vectorized operations on vector registers, utilizing our hardware, which is vector hardware. So this is simple enough, but if we try to do that naively for the triangular case, we have a problem. And what is the problem? The problem is that for each vector write, you either write it or you don't. But we want to work in a granularity of elements. We want this picture to look like this. If we do it naively, we get something that looks like a step function, or if the example was bigger, you'll see like a more coarse triangular. And that's not what we want. We want exactly the elements that we work on. So the solution here was to mask each of the vector stores. So you can see that now we have 3 kinds of elements on after the write. We have elements that are written, elements that are not written, meaning that we don't even iterate over them, and we have elements that are masked out. One thing that I forgot to mention, maybe I'll go back to the introduction slide, is that one naive elementary way to implement it is to feed the upper triangle with some elements, with some data, that will yield probability of 0. But we didn't want to do that. That was an option, but we didn't want to do that because performance. These models can reach tens, hundreds of thousands, sometimes even millions for the new models of elements. And if we have the chance to work on half the data, we'll take it. We need the performance. So going back. Okay, so I talked about vectorization, and the reason I remembered it is because note that there are some elements that we don't even iterate on. There's some vectors that we don't even iterate on, and that's great for performance. Next challenge, which is also a correctness challenge, relates to unroll. So again, Dafna just talked about unrolling a few minutes ago. And unrolling, again, for the traditional case looks like this. Dafna showed you a unroll loop of 2. And she also showed you unroll factor, of 2, and she showed you unroll factor of 4. And I'll show you unroll factor of 3, which is fine. Like you can do almost an unroll factor that will benefit you, will give you benefit. So what I want you to notice in this slide, we are still in the traditional case, in the rectangular case. I want you to notice that first, the unrolling is done on the I loop this time, the outer loop, and that all the iterations before the optimization work on the same number of vectors, in this case 2 vectors. This will not be the case for triangular access, as shown on screen now. You can see that the upper 4 iterations work on 1 vector, and the bottom 4 iterations work on 2 vectors. So, for example, an unroll factor of 3 will not work here, because within an unrolled iteration, we can only work on the same number of vectors. We cannot change that in the middle of an iteration, only between iterations. So the solution here was to restrict the unroll factors that we allow for the triangle access. And you can see the formula on screen on how determining if an unroll factor is valid or not. It's always with respect to some vector size. And once we do that, we can do unrolling, and we again want to gain the performance that comes with unrolling. This is like a basic compiler optimization. We basically saved all the overhead of performing the loop if we do less iterations. So as I said, we still want to do that even for triangle access, but we need to be more careful about which unroll factors we allow. Next challenge that I'll talk to you about is this time a performance challenge. It relates to parallelization and also topics that Dafna covered. If we take the triangular axis and parallelize it naively, the parallelization will look like on the left. This is how we do it. So you can think about if the rectangle was full, so each TPC will do the same amount of work. But since it's not a rectangle, it's a triangle, you can see that, for example, TPC 0 is idle for most of the time, and by TPC 3 they're doing a lot of heavy lifting. The solution was as seen on screen, to do some sort of interleave pattern for dividing the work, yielding a much more equal work division between the two, between all the engines of TPCs. So we have more than 4, but for illustration purposes, I put down 4 TPCs. I can show you now how it looked before the optimization, before this interleaving of work. You can really see the diagonal of the triangle. If you look at the first blocks, the pink blocks, you can really see the diagonal of the triangle. And for this specific workload, we talk about 220 microseconds. And after the optimization, so first you can see that everything is neatly packed, no idles, no bubbles in the process. And we drop to 170 microseconds. We got 22% speed up, which is massive, especially when considering that the optimization is relatively simple to grasp. Last issue that I'll talk to you about relates to fusion, which is the main task of our product, right? We are Fuser, we do fusion. So when Dafna talked about fusions, if you noticed, when we fuse 2 nodes together, all the bounds of the loops must be the same, right? Because you want to do the same work on the same elements, on the same memory. So this is like an implied assumption that is not longer correct, because the innermost loop bound is now dependent on the loop before. It's not the same, even if the dimensions are the same dimensions for the data, for the tensors, the loop will not run on the exact same number of elements. So this is the traditional case, and I put here a 2 element-wise operation, absolute value and add, and we can easily fuse them together. There's no concern about that, assuming, of course, that all the dimensions are the same. For the triangular case, things are a bit more complicated, and we had to pay attention to that too. For example, here we have, again, it's an absolute value and an add, but this time the add is triangular. And specifically, when the producer is element-wise regular, we can fuse them together into one fused node, which is also triangular. That's okay, because when we have a triangle operation, everything that's above the diagonal, the upper triangle, you can think about it as don't care. So we don't care if the result of the absolute value there. However, for the opposite case, where the producer is a triangular and the consumer is a rectangular, we cannot do that. And we can do that because the output of a rectangle operation expects valid data throughout all the tensor, including the upper triangle. So we can't give him don't cares to add with something else, in this case in 2. What we could do in this case, we could take the fusion and say that we fuse it as a rectangular node. But we don't want to do that most of the cases. If you haven't guessed why, so I'll tell you, performance. We rather iterate in a triangular manner on one and then iterate on the full tensor instead of doing a full iteration on both. So performance is like our bread and butter here. Okay, so to conclude this part, I presented to you the new kind of operation, which boils down to the new kind of access pattern, which we didn't have before. I presented to you 4 different challenges on 3 different levels: performance, correctness, and fusion. And this was like just a taste of what we do. There's a lot of challenges in this field, specifically for triangular softmax. There's still ongoing work, which is, for me at least, very interesting work. And there are challenges in these 3 fields and others. So we'll conclude the talk now. Thank you for now.
Thank you, Omer. So I think we've seen that we got some context about deep learning compilation. We saw what the TPC fuser is and how it's incorporated within the entire compilation graph flow. It is deployed as part of the Gaudi software stack. And we've seen that it has significant improvement for the entire system, and it's a critical part of graph compilation. And it works closely with the graph compiler. And I think we also saw some of the challenges that you also need to implement and to optimize every specific TPC kernel, but you also need to take into consideration the entire system and the way that graph compiler will be able to use these kernels in the most optimized way for the system. So thank you very much for listening.